Hello guys, I'm Charles, the uncle and facilitator in renal physiology series. Welcome to today's module, is module 6, and our topic of discourse is urine concentration and dilution. Alright, we'll look at what a concentrated urine is, or what a dilute urine is, why the kidneys either concentrate or dilute the urine, and how does the human kidneys concentrate and dilute urine. Now, sometimes you go to the restroom and you pass out very large volume of urine. Other times, when you visit the convenience, you may pass out very small volume of urine. It is not the oracle in your village controlling that. It is the kidney. So when the urine passed out is small, it means that that urine is a concentrated urine because it has less water in it and more solutes. But when the volume of the urine passed out is large, it definitely means that that urine is dilute or diluted because it has large water and less solutes. We'll look at the definition of terms before we proceed into the mechanisms of urine concentration. Alright? Good. Now, a concentrated urine is one with less water and more solutes. The volume of a concentrated urine is usually small. So when you go to the restroom to pass out urine and you find out that the urine is just few drops, it means that that urine is concentrated. The human kidneys concentrate urine when there is hypodipsia, that is low fluid intake, dehydration, low body water content, hypovolemia is low ECF volume, hyperosmolarity, that is there is high solutes, sodium ions in the blood, and during sweating, hot weather conditions. Oftentimes when you sweat, you visit the restroom less frequently. So these are the reasons why your kidneys concentrate the urine, why your kidneys makes the urine to be very small in volume. Alright? Now, a dilute urine is one with more water and less solutes. Okay? The volume of a diluted urine is large, very large. It's like you keep passing out the urine and it's never ending. It's like you want to wee the whole water out of your body. That urine is known as a diluted urine. When the water in the urine is in excess of solutes, the urine is diluted. The human kidneys dilute urine when there is polydipsia. That is, maybe you are taking in enough fluid. Sometimes, if you are observant, you find out that after taking like 1 liter of water, or let's say 1 bottle of Eva water, you see that you keep visiting the convenience frequently. That is because of polydipsia. When you increase fluid intake, the urine passed out will be large and dilute. Okay? Again, the human kidneys dilute urine during edema when there is excess body water content, hypervolemia when the ECF volume is so large, and in hypoosmolarity when there is low sodium ion content of the blood. Again, in cold conditions, when the weather is cold, you find out that you visit the restroom frequently. It is not the oracle in your village that is controlling all of this, but the kidneys. You will find out how the human kidneys concentrate or dilute urine after this discussion. Alright, going forward. In isotonicity or isosonic fluid, the osmolarity of the blood is same as plasma. In hypotonicity or a hypotonic fluid, the osmolarity of the blood is less than plasma. Whereas in hypertonicity, the osmolarity of the blood is greater than the osmolarity of plasma. Good. We'll look at the mechanisms by which the human kidneys concentrate urine. There are two basic mechanisms by which your kidneys concentrate the urine. The first one is known as the countercurrent mechanism. Number two is the vasopressin mechanism. We'll look at this mechanism in details. Beginning with the countercurrent mechanism. What is the countercurrent mechanism? It's a system of two parallel fluids in which the flow of fluid are in opposite direction to each other. This is an example of two parallel tubes. Alright, this is tube 1. Just a minute. This is tube 1 and this is tube 2. Okay, these are two tubes which are parallel to each other. Alright, now the direction of the arrow here indicates the flow of fluid in tube 1 and tube 2. You can see that the flow of fluid in the two different tubes are in opposite direction. In the first tube, the flow of fluid is in the downward direction, whereas as soon as the fluid makes a U-turn, remember this fluid is still coming down this way, as soon as it makes a U-turn, it begins to flow upwards. So this is an example of a countercurrent system. There are two types of countercurrent system or mechanism. The first one is known as the countercurrent multiplier system. The second one is known as the countercurrent exchanger system. We are going to look at them in details. But before then, the human nephron is a typical example of the countercurrent system. Alright, if you take a critical look of the nephron, I treated the nephron in module 1, you would see that there are parallel arrangements of the renal tubule. Alright, this part of the nephron is known as the descending loop of Henle. Okay, the descending loop of Henle is in parallel arrangement to the ascending loop of Henle. Again, so once the fluid comes from the renal corpuscle into the PCT and it enters the descending loop of Henle, as it flows downwards and makes a U-turn, it begins to flow upwards. So you could say that the flow of fluid inside the descending and ascending loop of Henle are in opposite direction to each other. Again, if you take a critical look of the ascending loop of Henle and the collecting dot, you see that the arrangement is also parallel. So the flow of fluid in the ascending loop of Henle is upwards. In the collecting dot, it is downwards. Alright? Beautiful. So a human nephron is the typical example of the countercurrent system. Good. Let's look at the countercurrent multiplier system. The countercurrent multiplier system is formed by the peritubular capillary of the cortical nephron. Take notes. Actually, this system establishes the medullary hyperosmolarity gradient, also known as the cortical medullary hyperosmolarity gradient. Alright, it is an active process. Okay, good. Going forward, we are now diving into the mechanism of urine concentration and dilution. Mechanism tells us how the human kidneys concentrate or dilute the urine. Alright, in looking at this, we'll first of all look at the normal plasma osmolarity of the blood, and then we'll look at the roles of the different renal tubules in the formation of a concentrated urine. First, we'll look at the role of the proximal convoluted tubule. Then we'll look at the role of the loop of Henle, and then we proceed to look at the role of the distal convoluted tubule. Then we'll look at the role of the collecting ducts, and then the role of urea in concentrating the urine. The normal plasma osmolarity of the blood falls between 290 to 300 milliosmol per liter. I mentioned this in the previous module when we did urine formation. Alright, 290 to 300 milliosmol per liter is the normal plasma osmolarity. Now, so in the proximal convoluted tubule, the osmolarity of the glomerular filtrate is 300 milliosmol per liter. In the descending loop of Henle, there is a gradual and progressive increase in the osmolarity of the glomerular filtrate. This is from 300 to 400, and then to 600, and then to 900, until it reaches a maximum of 1200. Now, in the ascending loop of Henle, there is a progressive and gradual decrease in the osmolarity of the glomerular filtrate. This decreases from 1200 to 700 to 400 to 200 until it reaches a minimum of 100 milliosmol per liter. So there is actually a change or alterations in the osmolarity of the glomerular filtrate as it flows through the successive parts of the nephron. Going forward, the role of the PCT. From these parts to these parts forms the PCT of the nephron. In the PCT, the osmolarity of the glomerular filtrate is 300 milliosmol per liter. This is normal. The PCT is permeable to both water and solutes. So water and solutes can diffuse out of the proximal convoluted tubule. Let's say, for example, if there is 100% of sodium ions inside the PCT and 60% of sodium ion goes out. Just a minute. There's 100% here, 100% of sodium ions in the PCT, and 65%, okay, let's use 60, and 60% goes out. 60%. 60% of sodium ion moves out. Alright, this is sodium ions. Sodium ion. Alright, there is 100% of sodium ion in the PCT and 60% moves out. It therefore means that 40% of sodium ions is remaining in the PCT. Alright, in the same way, if there is 100% of water in the proximal convoluted tubule and 60% goes out, this is another 60% of water. %60 of water moves out. Alright, it definitely means that 40% of water is remaining inside the PCT. So 40% of sodium ions and 40% of water is the same. Take note that the ratio of water and solute transport in the PCT is the same. Thus, there is no net change in the osmolarity of the glomerular filtrate in the PCT. It therefore means that the glomerular filtrate in the proximal convoluted tubule is isotonic to plasma. Alright, going forward. From this part of the nephron represent the descending loop of Henle. Alright, now in the descending loop of Henle, there is a gradual and progressive increase in the osmolarity of the glomerular filtrate. This is because the descending loop of Henle is permeable to water but impermeable to solutes. So water can freely diffuse out of the descending loop of Henle while sodium chloride cannot. Hence, the glomerular filtrate inside the descending loop of Henle is said to be hypertonic to plasma. This is the reason the descending loop of Henle is also known as the concentrating segment of the nephron. Because as water is leaving, there is less water inside the descending loop of Henle, and there is more solutes concentrating or accumulating in the descending loop of Henle. Hence, it is the concentrating segment of the nephron. Why is this so? Let me show you the mechanism briefly. Now,